Okay, continuing on in this monster of a section of the book. So, here are some theorems. A polynomial function with real coefficients, so a polynomial, can be factored into a product of linear factors. These are things that look like x minus a number. And irreducible quadratic factors. These are quadratics with no real root. Okay. Why this is true is a little complicated. It'll actually be covered in the next optional section, the section called complex roots of polynomials, which is not formally covered. There is a video about it. But what this theorem really says is, if I have a polynomial of really, really big degree, let's just say it's like 3x to the 7th minus 10x to the 5th plus x to the 4th minus 11x cubed plus 2x squared minus 12. It's a degree 7 polynomial. Can it be factored? Yes. And it will have some linear terms and some irreducible quadratic terms, but nothing else. That polynomials can always be factored down to just linear terms and irreducible quadratics. And those are the basic building blocks from which every polynomial can be built up. There's a side result that says if you have a polynomial of odd degree, it has to have at least one root. We actually already could say this from an earlier section about end behavior. So the reason why this second theorem is true, if you have a polynomial of odd degree, what's the end behavior? Well, it's opposite. So either it goes down on one side and up on the other, or the reverse. But somewhere in between is the axis y equals 0. So how on earth can my nice continuous polynomial go to negative infinity over here and positive infinity over here? It's going to have to cross and have a root. At least once. And that's what this says. A polynomial function of odd degree has at least one real 0. It might have more than one, but it definitely has one because it's got to cross that axis somewhere. Okay. And those are two fairly small results. That first one about linear and irreducible quadratics is actually a pretty big theorem, but we don't really use it very much in this course, so don't worry. So here's another theorem that honestly we don't emphasize very heavily. So suppose you have a polynomial and you want to find the zeros of it. That's a pretty recurring theme. And the rational roots theorem has given you a whole lot of possibilities. Some of them maybe are very big numbers. Okay. They can't all be roots. So suppose the leading coefficient is positive. In other words, when you write f of x equals an x to the n plus, etc., this number is positive. If it isn't, just multiply the whole thing by -1, and that doesn't change what the roots are, but it does make the leading coefficient positive. Okay. So if you pick a positive number, okay, if you do synthetic division by x minus m, and the third row of the process has no negative numbers in it, only positives or 0, then there are no roots bigger than m. So if you do synthetic division by x minus m, the third row in the process has no negative numbers, then none of the roots can be bigger than m. Okay, and the sort of flip side result of that is if you pick a negative number, do synthetic division, and the third row contains numbers that alternate between positive or negative, where 0 can be considered either, then m is a lower bound. There are no roots less than m. Okay. So here's a polynomial. Use that theorem to find the biggest possible root and the smallest possible root. Now there's a lot of things you could do, but the rational roots theorem gives us this list. Notice it's a lot, and it contains some pretty big numbers. Let's start with a small possibility. So what we're trying to do is we're trying to say none of the roots are past this point or this one. Okay, I'm trying to find all roots are trapped to be less than some positive number and bigger than some negative number. So think, would I rather be trapped to look for roots between -2 and +3, or between -428 and +82? I would much rather restrict myself to a small region. It's going to give me less places to look, so hopefully I'll find them faster. So that's why we're going to start with small numbers and hope that it works out. Okay. So we're going to do synthetic division by x minus 1. We're going to look at the third row and hope there are no negative numbers. If there are no negative numbers, then none of the roots can be past 1. However, if there are negative numbers, I move on to the next possibility of 2. If that doesn't work, move on to 3 and so forth. Then I can do the same thing with negative numbers. Start with -1 and work your way down. And what you're hoping for is that the third row of synthetic division alternates between positive or negative, where 0 can count either way. Okay, and on the next slide, there will be a table here. So here we go. If I do synthetic division by, so I'm doing x minus 1, we have a pretty big remainder. Aha, x minus 3 had a remainder of 0. That does mean I found a root. And so on. Okay. However, all of these entries are non-negative, which means that this is the biggest possible root. On the last one, this alternates negative, positive, negative, positive, negative. Oops, go back. This alternates negative, positive, negative, positive, negative. When you're plugging in negative numbers, that's what you're checking. Therefore, there are no roots beyond -3. Okay, we also happened to find roots. Hey, that's neat. But also, because this positive input gave me all positive numbers, and this negative input gave me an alternating list, they form bounds on how big the roots can be. So I'm going to go back a couple slides. Come on, here's the list of all possible rational roots. What we've just determined is that there are no roots bigger than 3 or less than -3, which means both positive and -6 are out, as are positive and -12, 18, and 36. These are just too big, which means my rational roots are actually restricted to this list. When we actually computed them, we found these were roots and those weren't. And now I have one positive and one negative root, so then I can factor out an x minus 3 and an x plus 3, not 13, sorry. That'll leave behind something. So I ask this. If I found x minus 3 and I factor out x plus 3, what's the degree of what's left behind? So I started with degree 4. Once I factor out x minus 3, I'll have degree 3. Once I factor out x plus 3, I'll have degree 2. Which means the problem is essentially done, because once you have a degree 2 thing left, just throw the quadratic formula at it and you'll be done. So this is a way to find bounds on how big zeros could be. This can also help you narrow down your search. This is not a technique that's ever required in any problems we put on exams. It can be helpful. Okay. The intermediate value theorem is the last thing in this section. We've implicitly used it before. If you have a polynomial that goes from a negative to a positive value, somewhere in between there's got to be a 0. Because it's a continuous function, if I go from negative to positive, I have to have a 0. So show that this polynomial does have a root somewhere in between 0 and 1. Spoiler alert, finding it is a nightmare. Just prove it exists. Well, if I evaluate f at 0 and 1, I get a negative number and a positive number. So if I was to try to graph this, f of 0 is -1, f of 1 is 2. How do I get from here to here? I have to cross the axis and have a root. So from the intermediate value theorem, it follows, yep, there's a root somewhere in there. The rational root theorem, by the way, would only be plus or minus a half. So something in between 0 and 1 would have to be a half, but that will not work. 1/2 is not a root. It doesn't mean it doesn't have a root there. It just means it doesn't have a rational root in between 0 and 1. It's going to be something really unpleasant. You could actually find it. If you manage to find the roots of this without using a calculator, so no decimal approximation, email me and I'll be impressed. Okay. So finally, how can I approximate the real zeros for a polynomial? Maybe I can't find it exactly like on that previous one. Maybe I just want to approximate it. Well, using the intermediate value theorem, maybe I find two consecutive integers. For example, in the last one, we used 0 and 1 and saw, yes, there's a root in between them. Maybe then, I don't know where it is, but what I do is I divide it into subintervals. I evaluate the function and try to find more specifically where it changed from positive to negative. And I just keep doing that. So can we find the positive real zero of this to at least 2 decimals? So we already know it's between 0 and 1, so divide it into pieces, 0.1, 0.2, 0.3, 0.4, and so forth. Evaluate the function at all points. OK. F of 0.1 is negative, f of 0.2 is negative, f of 0.3 is negative, f of 0.4, 0.5, 0.6, all negative, f of 0.7 is negative, f of 0.8 is positive. Therefore, the change from positive to negative happens somewhere in between there. So there is a root in between 0.7 and 0.8. Now, do it again. 0.71, 0.72, and so forth. But we find quite quickly, f of 0.70 is negative, f of 0.71 positive. Therefore, the root must have happened somewhere in between 0.70 and 0.71. So out to 2 decimal points, the root is approximately 0.7. This is not how your calculator does it. This is actually a terrible way of estimating the roots. This is like, I'm just going to keep guessing and checking until I get closer. The way your calculator actually does it is a very, very elegant calculus-based technique, which you may or may not learn if you take Calc 1. It tends to be a kind of labor-intensive, and it gets skipped from a lot of classes. I kind of hardly ever bother to cover it. It's called Newton's method of finding roots. That's how most people actually estimate roots, and it's a lot faster. So this problem here, for example, I have to do up to 10 computations to get the first decimal point, up to 10 computations to get the second. Every time I want to get a new decimal point, I have to do up to 10 computations. That doesn't scale very well. It starts to get very labor-intensive if you want to go further and further, because not only do I have to do 10 computations every time, but they get more intricate because they involve more and more decimal points. So the actual technique is a lot faster, called Newton's method. OK, so the topic of this video was these bounds on roots and then this estimating of roots. It's not something that's actually ever going to show up on exams, but it can be handy for actual practical use. So here it was. Anyway, that's the end of this section. I know it was kind of a beast. The next section, complex roots, is optional as well. There is a video on it. There's just one video for the whole section. Go ahead and take a gander if you're interested.